Hello and welcome to Empowered Learning. This video will be about inverse functions. In particular, we will talk about defining, graphing, and evaluating inverse functions, and how to determine whether we have an inverse function based upon the graph of the function. Let's start with question number 1. So question number 1 says, determine whether or not a function is one-to-one. So before we answer this question, we need to know what is a one-to-one function and why is that important when we talk about the inverse of a function. Well, it turns out that a one-to-one function is a special type of function to where every x value has a unique y value that it corresponds to. So as an example, let's say we have a mapping here. So let's say we have a set of x values. We'll just say 1, 2, 3. And we have y values over here, 4, 5, 6. Now, if we had this situation where we had a mapping that looked like this, and we will, so yeah, if we had this, then this would constitute as a function. And we know that because the definition of a function is that we have two non-empty sets, namely x values and y values, that are related to each other such that every x value has exactly one y value that it corresponds to. Okay? Now, if we were to come up with another type of mapping to kind of show what is not a function, then it would look something like this. And of course, here the reason why this mapping is not representative of the function, because our 1 right here corresponds to more than one y value. Okay? In other words, one person can't be in two places at the same time. Now, we are saying that this mapping is a function, but we cannot call it a one-to-one function, because a one-to-one function by definition is a special type function where every x value corresponds to a unique y value. And you see here that this x value and this x value, 1 and 3, both correspond to 4. 1 does not have a unique y value that it corresponds to because 3 also corresponds with 4. And so the reason why this would not be considered a one-to-one function is because of this fact. When we say we have a function that's one-to-one, we're essentially saying that if we do a mapping from x values to y values, it would be a function. And if we flipped everything around and related everything from y to x, it would also be a function. Now notice if we actually flipped everything, it would look like this. And of course here 4 would correspond to 1 and to 3, and 2 with 6 will correspond to 2. And we see here that now the y values are in the place of the x values. We have one quote-unquote x value corresponding to 2 y values now, and everything is flipped. And so one-to-one functions are essentially saying that, hey, whether I look at it in terms of mapping x to y or mapping y to x, I still have a function. In terms of the graph of just a graph in general, we know that we have a graph of a function whenever that graph passes both the vertical line test that you're probably already familiar with and the horizontal line test. So for example, y equals x squared looks like this. X squared does pass the vertical line test because any vertical line would intersect the graph only once, but it does not pass the horizontal line test because we have two places where that horizontal line would intersect the graph. So what that's telling us is that although this is a function, it is not a one-to-one function. Okay? An example of a one-to-one function would be something like x cubed, which looks more like this. And so here, this passes the vertical line test as well as the horizontal line test, meaning that any vertical line will intersect the function once, any horizontal line will intersect the function only once. So that's what constituted as being a one-to-one function. So now that we have that introduction, we can now clearly answer question number 1 and determine whether it's a one-to-one function or not. All right, so for this particular function, the easiest way to test to see whether it's a one-to-one function is to graph it. And so we know that x minus 1 quantity squared just looks like x squared, but is a horizontal shift to the horizontal shift to the right 1 unit. So that would look something to the order of this. Now, this says that our domain is restricted for values of x being greater than or equal to 1. So that means all of my values that are to the left of, well, all my points that are to the left of x equals 1, I have to get rid of. So this is what my resulting function would look like. And of course, if we do the vertical line test and the horizontal line test, we see that it will pass it. So yes, this would be a one-to-one function because every x value would correspond to a unique y value, and we test that graphically by doing the vertical and horizontal line test. All right, let's move on to question number 2. So for question number 2, we want to determine whether this piecewise function is a one-to-one function. And again, the easiest way to figure this out, in my opinion, is just to graph it. So we have a piecewise function where the graph looks like 2 pieces of 2 lines. So we'll just kind of construct this right quick and then we'll see what we're working with. So our major points of transition here are at -1 and at +1/5. So here we know that our function first looks like the line x plus 8 for all values of x that are less than or equal to -1. So we know that this line is going to be a line with a positive slope because here we know that the slope is understood to be 1, but it's going to stop whenever x is equal to 1. So our line is going to look something like this. And so what we need to do is figure out where this actual point is going to be. And to do that, we can just take -1, plug it into our function, and we see that -1 plus 8 would just give us a +7. So let's say here we'll have 7. So our graph is going to look something to the order of this. Okay. Now, for the second piece also looks like a line with a positive slope, but of course it's 5 times, the slope is 5 times as high as our first piece. So I guess in saying that, let me kind of adjust this line here to make it look a little better. So we could say something more along the lines of this with this first line. So with the second line, of course, we start at x is equal to, well, x has to be greater than or equal to 1/5. So we know that this is also going to be a line that looks like this, but we're going to have a place where it starts. And again, if we plug in 1/5 into here for x, then 5 times 1/5 plus 6. 5 times 1/5 is 1. That'll be 1 plus 6, which is 7. And so we're starting here again at 7. And so from here, we have a line that goes up, let's see, twice as fast. Yeah, so, but that would be here at 1/5. and our line would look something like that. And so now we ask ourselves, based upon what we see, is this going to be a one-to-one function? The answer to that question is no, because when you look here, you'll see that this line this function passes the vertical line test just fine. But the issue is whenever we talk about the horizontal line test, it passes it here, but right when y is 7, you see that this function is intersected twice. So for that reason, we know that this is not a one-to-one function. Moving on to question number 3. We want to determine whether our functions f and g are inverses of each other by evaluating the composition of f and g and of g and f. Now, what this is talking about is we've looked at graphical ways to determine whether a function is one-to-one, namely the vertical and horizontal line test. We've also talked about the definition of what a one-to-one function is, meaning that we have a special type function to where every x value corresponds to or matches up with a unique y value. When we want to algebraically show that that two functions are inverses of each other, what we do is we say, if we can take, let's say, some function f and the proposed inverse, if we can stuff the inverse of the function into the original and get x as an output, and also take the inverse function and stuff the original function f into it and get x as an output, then algebraically what we are showing is that every x value has a unique y value that it corresponds to. And so this is essentially what this question is asking us to do with this function f and g. So we're just going to work out what the composition of f of g of x is and what g of f of x is. And if we do not end up with x in both situations, then we know that it is not those functions aren't inverses of each other. All right, so let's start with the f of g of x, which will look like this. And of course here, this means everywhere where we see x in our function here, we're going to replace it with g of x. So we're going to have r times, and then g of x is tx minus s over r plus s, and then divide all that by t. And of course we need to reduce this to see if we get x as an output. So coming here, we know that this r and this r will end up reducing to 1. And that will leave us with t times x minus s plus s, all that divided by t. And of course, minus s plus s, that cancels to 0. And we just have t times x divided by t. And of course, our t's here reduce to 1. And our result is x. So we see that this works out. When we work on g of f of x, we'll now do the reverse. So now here for g of x, everywhere where we see x here, we're going to replace it with everything here. So we'll have t times, and in place of x, rx plus s divided by t. And then all of that is divided by r. Similar to what we did earlier, we see that these t's reduce to 1. And we just have r times x plus s. Oh, I forgot the minus s here. So let me, forgot about that. Sorry, y'all. So you have a minus s that's here. And if we continue, we have r x. Let's try to get this right. Rx plus s minus s, all divided by r. And from here, positive s minus s cancels to 0. We'll just have Rx divided by r. Of course, the r is reduced to 1, and we just end up with x. So in both cases, we end up with x. So we know that these functions are indeed inverses of each other. All right, let's move on to the next question. All right, so for our next question, we're considering a function f of x is equal to 6 minus 7x, all that over 3x. And we're asked to find out what the inverse of that function is, as well as what the domain and range of the original function and the inverse. So one of the things that we need to be aware of is, number one, how do we find the inverse of a one-to-one function? So we're told here that this function is one-to-one. So what we can do here is just replace f of x with y. And the procedure for finding an inverse function is that we want to first interchange the positions or the places of x and y. So everywhere where you see y here, it will end up being x. Everywhere where you see x, you will replace it with y. Now, why would you do that? No pun intended. Well, remember the definition of a one-to-one function is that we have a function where every x value corresponds to a unique y value. And if you remember the mapping that I was telling you about, we basically had a situation here where if we have a function where we have points x, y on it, then every x value will have a unique y value. So in turn, what that means is if we were to flip or interchange the positions of the x and y coordinates for a particular relation, if that relation was a one-to-one function, then when we flip the x and y coordinates, the result that we would get graphically or in a mapping or in a set of ordered pairs would still end up being a function. Okay, so that's why we need to interchange the positions of x and y here. Now I'll go ahead and erase this and we'll make that happen. So here we're going to say that let x equal 6 minus 7y over 3y. And now from there, what we need to do is just solve for y. And when we solve for y will actually end up being our proposed, well, not our proposed, but it'll be our inverse function here. So we're just going to solve for y. I'll divide this by 1 and cross multiply to make this simple. And so that'll be 3 times xy equals to 7 minus y. And of course, we need to get all terms with y on the same side. So we'll add 7y to both sides. That will cancel. We'll end up with 3xy plus 7y, which is equal to 6. And then from there, we know that here we need to factor out y, both terms. So that'll be 3x plus 7 equals 6. And then we just divide both sides by 3x plus 7. Excuse me. And so this will end up being our inverse function. So we have 6 divided by 3x plus 7. That would be our inverse function. Now, going back to what we were talking about earlier, which is if we have a function that is one-to-one, then if our original function has points x, y on it, then our inverse function has points y, x. So What this tells us here is that the domain of the original function is all the x values, and the range of the original function are all the y values. For the inverse function, it is just the opposite since we switched everything. Okay? So the domain is whatever the y values for the original function are, and the range is whatever the x values were for the original function. Okay? So once we find out what the domain of the original function is and the domain of the inverse function, then we will know essentially what is the domain and range of both functions. Now, if we look at our original function here, we notice that the only restriction that we will have is that x is not allowed to equal 0. So that means that the domain for our original function is going to be all real numbers except for 0. If we look at our inverse function here, also we can look here, we know that the only restriction that we have on this function, and I'll come over here and work it, the only restriction that we have here is that our denominator can't equal 0. And of course, if we subtract 7 from both sides, we'll get 3x is equal to -7, divide both sides by 3, and we get x is equal to -7/3, not equal to -7/3. So here, what this is saying is that we can have any real number in our range except for -7/3. Now, since we have this relationship here, that we have the domain of the original function, range of the original function, here we know that for the inverse, everything is the opposite. So here we know that for the inverse, whatever the range of the original function is going to be that. And over here, whatever the domain for the original function will now be the range. Okay? And I'll write that differently so that we can kind of see what's going on here. Use this in a different way. So essentially what we're saying is that the domain of the original function is equal to the range of the inverse, and that the range of the original function is equal to the domain of the inverse. That's essentially what we're trying to say here. So with that being said, we can now answer these questions. So the domain of the original function is going to be all real numbers except for 0. The range of the original function is going to be the same as the domain of the inverse, which is all real numbers except for 7/3. The domain of the inverse function is the same as the range of the original function, which is all real numbers except for -7/3. And the range of the inverse function is the same as the domain of the original, which is all real numbers except for 0. And so that's how we answer these questions and decipher what's going to be the domain and range of the original function as well as the inverse. Now for our next question, we're asked to use the graph of the original function f to sketch the graph of the inverse. Okay. Now, simply put here, if you remember, we said that if a function is 1-to-1, then it will have an inverse. And that means that for every point x, y you have on your graph, if your graph is a 1-to-1 function, you will be able to interchange the x and y values and produce another function. So in this case, let's list all of our values here that are given to us, so, or points rather. So we have the point -3, -6. So that means for the inverse function, this will be -6, -3. We also have the point 1, 4 here. So for our inverse function, this will be the point 4, 1. And then we also have the point 3, 5. So that means for our inverse function, we'll have the point 5, 3. And so now, essentially, all we have to do is plot these points and draw, and we'll see that we'll see what we end up having as far as the inverse function, and then we can just choose. Okay. So instead of looking at the graph here, I'm just going to draw it first, and then we'll look at the graph. All right, so here we need to graph the point -6, -3. So -6, -3 would be about right here. We also have the point 4, 1, which would be here. And we also have the point 5, 3, which would be here. So if we put this graph together, it would look something in the order of this. Go up like that. And as you see, and we haven't talked about this, but we'll talk about it now, and this is part of the reason why I wanted to draw this graph. Whenever we say a function is one-to-one, meaning that it has an inverse, whenever we did this interchange of x and y values going from here to here, what we're actually doing from a geometric perspective is we're reflecting our original function here, the blue one, about the line y equals x. So when we interchange x and y coordinates, what we're actually doing is reflecting a function about the line y equals x. And so that's why in your pre-cal or college algebra courses, learning about the line y equals x is so important, because not only is it a basic line that you need to know, but is also instrumental in being able to conceptually understand what you're doing whenever you find the inverse of a function. Okay. Now, that being said, now that we know what the graph looks like, we know that the best answer choice would end up being C here, because this is the one that looks most like what we've drawn. All right, so for our next question, it asks us to use the graph of the function that we're given to answer the following questions. Namely, what is going to be the domain of the inverse function, and what is the range of the inverse function? Okay. So to do that, what we can do is actually figure out what the domain and range of the original function is, and then we know that since this function is a one-to-one function, because it passes both the vertical and the horizontal line test, we can just interchange those relationships to come up with the domain and range of the inverse. So if we look here, we see that the domain of this function will start on the lower end at x equals -6, and it'll keep on going until we get to looks like 5 here. Okay, because of course this is 7, 6, 5. So the domain of our original function is going to be from -6 to 5. The range of our original function, of course, our lowest y value is 1, 2, 3, 4. On the lower end at -4, and on the upper end it looks like 6. So on the lower end -4, on the upper end 6. So we know that if this is true, then if we're talking about the domain of the inverse, that's just going to be the same as the range of the original function. And if we're talking about the range of the inverse, that is the same as the domain of the original. So Here, if we find the domain of the original is the same as the range, which is from -4 to 6 with brackets, and the range of the inverse is the same as the domain of the original, which is from -6 to 5. So for our next question, we're asked to use this graph to figure out what is going to be the y-intercept of the inverse function. Okay. Now, if we think about it, we want to find out the y-intercept for the inverse function. So if we're looking at this as x, y, and y, x, where this is the inverse, and that is the original function, then of course my y-intercept is going to look something of this nature here. So that means if I go back this way, it's going to look like an x-intercept. So my point is that if we want to find what the y-intercept of the inverse function is, then that's like asking us what is the x-intercept for our original function. And if we look, the x-intercept for our original function is here, and that is at the point -3, 0. Okay. All right, let's move on to question number 8. I'll just scroll up. So for this question, is asking us to evaluate several values of the inverse function. And of course, for here, the way that it's written is kind of the goal here, is we want to know what is going to be the inverse function at 0, what is the inverse function evaluated at 4, so on and so forth. Okay. Now, again, what we see here, if we keep the relationship again as xy being your original function and inverse being this, then whenever we're asked f inverse of 0, let's say for this first one, it's kind of like saying this. So f inverse of 0, this is like asking for a y-intercept for the inverse, which is like asking for an x-intercept for the original function. Okay. So here this is asking for what is the x-intercept for the original function here. Okay. So our x-intercept, as we see, will be at looks like -2, 0. So of course this would end up being the value of -2 at the end of the day. And the reason for that is that on our original function, we would have the point -2, 0, x, y. For the inverse, if we flip that, that would be 0, -2. Okay? And so this is asking, essentially, if this is in the x value position, what is going to be the corresponding y position? And of course, the inverse, we flip everything. So it's really like asking if we'll tell you what y is, you give us x. Okay. All right. So for b, we'll do the same thing. So f inverse of -6, it's kind of like saying, hey, on the inverse side, if we have -6 for x, give us y. But if we flip that, that's kind of like saying, if y is -6, give us x. And so here, if we look, when y is -1, 2, 3, 4, 5, 6, corresponding x value looks like it is -4. Yep, -4. So here, this would be -4, -4, and the answer to this would be -4. Similarly speaking, same situation here. This literally is like saying, when y is 4, tell me what x is. Okay. So here, when y is 4, so we go 1, 2, 3, 4. When y is 4, what is x? That'll be this corresponding x value here, which is 1, 2, 3, 4. And for this last one, this is like saying when y is 3, tell me what x is. So here when y is 1, 2, 3, my x is 0. So you kind of get the idea of how to evaluate this now based upon the information that's given. All right, so moving on to question number 9, we want to write an equation for the inverse function given that the function that's given to us is a one-to-one function. So I'm going to come up here and work this. So here we know that we can let f of x equal y. So we have y equals 7 minus 5th root of x minus 1. And just like we talked about earlier, we said that in order for us to be able to find the inverse, the first thing that we need to do is interchange the position of the x and y variables. So here, everywhere where we see x, we put y and vice versa. And of course, our goal here is to solve for y now. So to do that, we would need to subtract 7 from both sides. We'll get x minus 7 equals a negative 5th root of y minus 1. If we multiply both sides by a negative 1 here, or divide both sides by a negative 1, then that would make this negative x plus 7, and that would be the 5th root of y minus 1. Let's make that 5 look a little better. And so now from here, come up here, we'll turn this around as 7 minus x. And then from here, we will take the 5th root, sorry, not the 5th root, but we'll raise both sides to the 5th power. And what that effectively does is get rid of our 5th root sign here. We'll just have y minus 1. And this will be 7 minus x raised to the 5. And then we'll conclude by adding 1 to both sides here. And we'll end up having 7 minus x raised, all that raised to the 5th, plus 1. And this is what our inverse function will look like. So our answer here will be 7 minus x, all that raised to the 5th, plus 1. Okay, and so for our last question, we're asked to look at this quadratic function with this restricted domain and to figure out what the inverse function will be for that. Now, for this question, we're going to have to rewrite our quadratic function in another way in order for us to be able to get it into a form that's conducive to us to find the inverse easily. Okay. Now, we know that quadratic functions in its canonical form looks like this, but we also can rewrite them in what we call the vertex form. Okay. And traditionally, we do this by doing the process called completing the square. So we do have formulas for that, and I'm going to use it here. We know that in this case, the relationship in between this form of the quadratic function and this one is that h is equal to negative b over 2a, and that k is f of negative b over 2a, meaning whatever value we find here, we just plug it into our function. We do have an alternative formula for that, which is 4ac minus b squared all over 4a. And so I'm giving you these formulas here because this is an alternative way to do what I am about to do, which is completing the square here. I'm going to do it the more traditional way here. But if you can't follow that, then of course you can do what I'm doing here. Now, the more traditional way of working with this particular quadratic is we want to try to force a perfect square here. So what we're going to do is do x squared plus 14x, and we need to come up with an expression here that's going to force this to be a perfect square. And we'll do plus 44. Now, since we are introducing a term, and I'm just going to put the number 1 under here to keep this labeled, then what we need to do is also subtract the same from this expression so that everything remains equal. Okay. Now, the process for completing the square is, it says whatever this middle number is, you divide it by 2, and then you square it, and that's what ends up being here and here. So you'll see that if we do that, we end up getting 49. So we'll put 49 here, 49 here. And when we factor this out, this automatically factors out to x plus 7 quantity squared. And then, of course, this will be plus 44 minus 49 will end up being negative 5 as a result. Okay. And so here we know that whenever we're doing completing the square, this particular expression here will always factor out to x plus a, and I'm going to call whatever's inside the parentheses here a. It's always going to be that square. Or another way that you can think about it, I'll erase this part, is to say that whatever b is divided by 2 squared. So it always ends up factoring out to be there. All right, so now that we have this, if we just replace f of x with y, then we can go through that process again of finding the inverse function. So this is y. Then, of course, if we interchange x and y, we have this situation. And now we can solve for y, and we know that when we end up solving for y, it'll end up being what our inverse function is. Now, before we move forward here, there is something that I want to make sure that we understand, because there is a change of variable happening, or interchanging a variable happening. And of course, that's going to affect us in our process to figure out what our inverse function is. So to do that, we know that whenever we solve for y, we're going to end up with our inverse function. So I'm just going to erase this from that. Now, remember that our original function has a restriction on its domain such that x has to be greater than or equal to negative 7. Okay. Now, when we interchange the x and y values, that means that what x was is what now y is. So now we have our restriction on our y instead of our x when we do the interchange. Okay. And so now when we solve this, we're going to keep this in mind. So solving for y now, we'll add 5 to both sides, and we'll have x plus 5 equals y plus 7 quantity squared. And at this point, we can take the principal root of both sides. So this will be plus or minus square root of x plus 5. All that equal to y plus 7. Go ahead and scroll down a bit here. So now at this point, we realize again that y has to be greater than or equal to negative 7. Okay? And so if y is going to be greater than or equal to negative 7, so that means we'll be plugging in values like negative 7, negative 6, negative 5, negative 4. Okay? And of course, if we plug values into here like negative 7, negative 6, negative 5, negative 4, this is going to give us non-negative quantities. So here, the answer choice that we choose here has to end up being non-negative. So what that means here, that we have to choose the square root of x plus 5. And of course, this result will give us non-negative quantities, just like this y here. Whenever we plug it in for several values of y, we will get non-negative quantities. And of course, now from here, we just solve for y by subtracting 7 from both sides. And here y, which ends up being our inverse function, is going to be square root of x plus 5 minus 7, with the understanding that y is greater than or equal to negative 7. So this would be, didn't mean to do that. So this would be the answer here to our question. And of course, we don't have to include this part. It is implied, but we needed that to be able to figure out whether we needed to choose the plus or the minus here. And so with that, this concludes the video that I have on inverse functions. I hope this has helped you. And if you like this video, please let me know that. And if you have any questions or requests for any other videos, please let me know. Take care.